Hey everyone, welcome to my channel. If you are interested in speaker design and improving sound quality, subscribe and join us. Hornresp, a very low volume software that simulates the horn projects. Today, we're going to simulate a Hypebolic or hyperbolic horn in this software. If you want to design your DIY transmission line, watch this video till the end. In the next video, we're gonna simulate a back-folded horn in acoustic. All the steps in acoustic are according to this video. The theory that we're going to work on is to design a straight horn. After that, we fold it to occupy less space. Click on the Add button to add the driver to the software, then double-click on the first cell and enter all the specifications of the desired driver. Note that SD is the effective area of the diaphragm and is determined by the radius of the cone. Enter all the specs, then click on OK. If the specs don't include X max and P max, leave them. Now follow this direction and choose Hypebolic with driver. Choose the first frequency equal to the driver resonance frequency, then multiply it by 4 and write it in the second blank. We're not going to use the default setting. Choose the first blank equal to the driver area and the next must be filled according to the previous tutorials. As you know, the length of the Hypebolic horn or hip in Hornresp is determined by this formula. Just enter the value obtained by the formula in centimeters. If you want to design a Hypebolic horn with an Excel file, watch it. Of course, you can set the T at 0.7 and try different values of S2 to get the F12 equal to 80 Hz. F12 is the cutoff frequency. If you want to design your own horn based on the said Excel file and save time, just set the frequency at 80 and the driver radius at 4.6 and get the S2 at 1.07 meters of the length of the horn. This is the side view of the horn with all the parts. Although we're not going to use the rear chamber, it is good to know VRC is the volume of the rear chamber in liters and LRC is its depth in centimeters. FR is the rear chamber acoustical lining resistivity in rails per meter, which is determined by the material that you want to use in the chamber, and TL is the thickness of the said material in centimeters. VTC is volume of the front chamber in cubic centimeters, and ATC is its cross-section area in square centimeters. Set VTC and a TC at 0 and click on the Calculate button. Since we removed the front and rear chambers, the resulting horn is without them. Follow this direction to see the frequency response of the horns. As can be seen, the sound wave travels in two directions. The first is the sound traveled by the direct radiator, and the second is by the horn. We should know the front of the cone and its rear side generally have a 180 degree phase difference. Considering the horn length, due to the 180 degree cancellation, the resulting response of this system contains nulls. As you can see, the response contains nulls. The first null is calculated by this simple formula. The first null on the graph is very close to the value obtained from the formula. Another way to design a transmission line is to use the transmission line tool of the software, although it doesn't include the Hypebolic horns. I apologize because in this video called it parabolic wrongly because of the similarity of their names. On this menu, select horn S1 S3. S1 is the cross-section area of this section in square centimeters. S2 and S3 are illustrated as well. S3 is the cross-section area of the horn mouth. L12 is the length of the first part, or the length between S1 and S2, and L23 is the length of this area. Set S1 and S2 as big as the driver cone area, then the area of the horn mouth, which was 1111. Since the tool doesn't contain Hypex or hyperbolic, select exponential with a few clicks. Exponential is a Hypex with t equal to 1. After that, select power on this menu to see the response. As can be seen, the response is the same as before. Before explaining the next part, I move the L12 slider to create two sections. Then I select filling and method. The first slider is related to the damping of the different materials. The higher the value, the higher the damping. Its unit is rails per meter. Many DIYers use Rockwell for subwoofers, but for full range speakers, it's better to use material with a lower damping value, because the damping material can kill the bass. If rails per meter is not familiar to you, you can search for materials based on their density. Pascal second per square meter at the top of the fourth column equals rails per meter, and the equivalent value of its density in kilogram per cubic meter is shown. For example, the first product with a flow resistivity of 5,800 rails per meter has a density of 14 kg per cubic meter. The link to this table is in the description. The link only shows the source of this information and nothing else. Note that the density in kilogram per cubic meter and flow resistivity in rails per meter, or Pascal second per square meter, are changed for different manufacturers. The next slider adjusts the length of the damping material of section 1. 100% means the whole section 1 is filled by the damping material. The next two sliders do the same for section 2. Now, I set the L12 at 0 and try to fill the horn with acoustic material. As you can see, the nulls in the response have been reduced, but the low frequencies are weaker than before. Since we designed an 80 Hz horn, the response should be extended to 80 Hz, so we need a method to reach it. To remove the nulls, there are some tips. The first is to use an enclosure before the horn throat. Many manufacturers and DIYers put the set enclosure before the horn. This simple formula calculates the required volume of the enclosure. This formula is indeed the relationship for a vented box. Another benefit of the enclosure is to extend the frequency response to 80 Hz. Enter a desired value for ATC. Note that don't use very big numbers. I use 1000 and the resulting enclosure will have a depth of 4.8 centimeters. The enclosure is added to the horn. Now, it's time to see the new response. If we compare the result with the previous response, we'll find out that all the nulls have been removed, and the response has been extended to 80 Hz. There is a huge null here. We can reduce the depth of this null by some tips that I'll explain in another video. As you know, this figure has two parts, a direct radiator and a horn mouth. We can see their responses separately. If you note the frequency response of the direct driver, you'll understand there is a deep null at 80 Hz. The null of the direct driver is the useful effect of the horn, which means the direct driver consumes less energy, and the horn is a complement to the direct driver. We can also see the response of the horn and combined, which is the summation of both responses. Don't forget to like and subscribe. Wait for the next exciting content.